This is the velocity profile of a fluid flowing downhill in a rectangular channel which is open on top. We can see that the speed is 0 around the edges of the channel, and the fastest point is in the middle on top. But how do we get here? How do we calculate what this flow should look like? There's already lots of maths out there about flow in circular pipes, but not much about rectangular ones. So in this video, we're going to take a look at the maths behind it and see where it takes us. But before we can get stuck into the 3D problem though, we need to quickly start with a simpler 2D version. Imagine we've got some water flowing down a slope from left to right. Now we need to know alpha, the angle of the slope, and also h, the height of our layer of fluid. We'll use y to denote where we are in the fluid, with y equals 0 at the top and y equals minus h at the bottom. You could put y equals 0 at the bottom, but the algebra works out slightly nicer this way. And then we'll call the fluid's velocity u, which will only depend on y. And the reason it only depends on y is because we want to look at the steady state flow, where the fluid isn't speeding up or slowing down as it moves along. It's reached a steady speed and it stays there. Now we've got our problem set up, we need some equations to help describe it. And for that we'll use the famous Navier-Stokes equations. These are actually a pair of equations, and I'm not going to go into too much detail here about where they come from, but the left equation comes from the conservation of momentum and the balance of forces acting on the fluid, and the right equation represents the conservation of mass for an incompressible fluid such as water. Now, the only pressure will be hydrostatic pressure that varies with the depth of the fluid, and this doesn't affect the flow at all. So we can ignore the pressure gradient term. And as I said, we're looking at steady state flow, so we want to ignore the acceleration term on the left as well. However, if we look at the values of the constants involved, for water, the density ρ is about 10 to the 3, whereas the viscosity, or how sticky the water is, μ, is roughly 10 to the minus 3. And this means that unless the flow is perfectly steady and smooth, and we have what's called laminar flow, the leftmost term will be very big, and we can't just ignore it. And this is where we need to quickly talk about the idea of the Reynolds number. Now, in this formula, u is the typical velocity scale for the problem you're looking at, and L is the length scale. So larger, faster flows have a higher Reynolds number than smaller, slower ones. And what makes the Reynolds number so useful is that it tells you whether you have nice, smooth laminar flow or wild, unpredictable, turbulent flow. And it's very difficult to do much maths when the flow is turbulent. So we'll assume the Reynolds number is small enough that we have laminar flow, which lets us cross that term out for now and crack on with some proper maths. So we can write our simplified equation down, and the force F is just going to be g sine alpha, the component of gravity down the slope. Now we'll tidy it up by combining all the constants into just one, and we're ready to solve it. So in the 2D case, u only depends on y, so that gives us our differential equation, and we need some boundary conditions to go with it. And on the bottom surface, at y equals minus h, we have the no-slip boundary condition u equals 0. At the top though, where there's only air above, we say the air exerts no shear stress on the fluid, which gives us the free slip condition du by dy equals 0 at y equals 0. Then to solve this, we can integrate a couple of times and use the boundary conditions to find the constants, and we get that the solution is a quadratic. And if we want to find the maximum velocity, well, that's where y equals 0, so at the top of the fluid. And the other measure we're interested in is the average velocity across the height of the fluid. So to find that, we need to integrate the velocity over the height to find the total flux, often called q, and divide that by the height h. And if we do that, we find the average is gh squared over 3, so 2/3 of the maximum velocity, which makes sense. If we'd calculated an average that was greater than the maximum velocity, or had different units, like if it was gh cubed instead of gh squared, we would know that obviously that can't be right, and we must have made a mistake somewhere. It sounds obvious, but these type of common sense checks are really useful. So now we're ready to move on to the 3D problem. And if we're looking at a cross-section through the fluid, the height is still h, but now we've also got an x-coordinate, the width, which we'll label 2w, because that way we can put our origin in the centre at the top, and the two sides will be at x's plus w and minus w. Now, this time the left-hand side of our equation, del squared u, or the Laplacian of u, has two terms. And we've also got four boundary conditions. The velocity is 0 on the left, the right, and the bottom, and we have the zero stress condition on the top. Now, solving this equation is quite a bit harder than it was in the 2D case, but if we can get rid of that minus g so that the right-hand side is 0, we'll have a homogeneous equation which is much easier to solve. And specifically, we'll have something called Laplace's equation, and there are methods that we can use to solve that. So the first step is to find a solution to this equation and not worry about the boundary conditions. And that's called our particular solution, which we'll write as UP. And the solution we've just found for the 2D case works as our particular solution here. And if we write down its values on the boundaries, it does actually satisfy the bottom two BCs, but just not the top two. But that's fine, because now we're going to solve the homogeneous equation and find another solution, the general solution, which can satisfy the BCs. And we'll call this solution UG. Then we'll be able to add the two together, and that solution will fit everything, both the differential equation and all of the boundary conditions. So we need to work out the new boundary conditions for our general solution, and it will need to balance our particular solution on the left and right boundaries at x is w and x is minus w, so that when we add them together we get zero velocity there. Now to actually solve Laplace's equation, we're going to look for a separable solution of the form f of x times g of y. And if we plug that assumption in, we can do some rearranging to get an equation where the left-hand side only depends on x, and the right-hand side only depends on y. And this step wouldn't work if we still had that minus g floating around and getting in the way. But because we've got two things which are equal and have no variables in common, they must be constant. And we'll call that constant lambda. And that observation lets us split this into two equations, one for f of x and another for g of y. We'll rewrite our boundary conditions in terms of f and g, because we'll need those in a second. And now we're ready to solve our pair of equations, but that will depend on the value of lambda. Specifically, we've got three cases. Lambda is 0, lambda is less than 0, or lambda is greater than 0. Let's start off with the simplest case when lambda equals 0. Then we just have that f and g are both linear functions, and we need to figure out the constants. So if we pay attention to the bottom two boundary conditions, the fact that g dash of 0 equals 0 means that c must be 0, and g of minus h equals 0 means that d must be 0 as well. So g of y is 0, which means that this solution is just 0, because remember, we're multiplying f and g together in the solution. So we can ignore this case. Next we have lambda is less than 0. And if you want to work out the form of the solutions for this case yourself, then pause the video and go for it, because this is a really useful one to know. So for f of x, we get some combination of sine and cos of root lambda x, and g of y is the same, but with the hyperbolic trig functions sine and cos. And if we turn our attention back to the boundary conditions, g dashed of 0 equals 0 means we need c to be 0, because sine has a non-zero derivative at 0. And then the only way we can satisfy g of minus h equals 0 is if we have d equal to 0 as well, because cos is always greater than 0. So again, we can ignore this case. Finally then, we have lambda is greater than 0. And since we've swapped the sign of lambda, our functions f and g basically just swap round as well. And again, if you want to try and work out which terms are 0 and which ones we can keep, then have a go before I tell you in a second. So once again, g dashed of 0 equals 0 means that c must be 0, because sine has a non-zero derivative at 0. But we can't rule the second term out, because the cosine function does have some zeros. Looking at f of x as well, we can see the boundary conditions are symmetrical on the left and right boundaries, and cos is an even function, so it's symmetrical about the y-axis, whereas sine is not, so the only possibility is to have a equals 0. Great, so we've narrowed down our solution to just one form, so we can multiply f and g back together again, and we'll simplify the constant and just call it a, and we can write the boundary conditions back in terms of ug. Now, the bottom boundary condition is automatically satisfied by the way we chose our functions, but the one above it isn't. To meet that condition, we need cosine of minus root lambda h to be 0, which means that root lambda h must be an odd multiple of pi by 2. And if we write that properly in terms of an index n, it's clear that we've actually got infinitely many possible values for lambda. So which one is it? Well, it's actually all of them. In the same way that we're going to add together our particular and general solutions, we can add together any combination of these cos times cosine terms to meet our remaining boundary conditions. So that means our ug is now an infinite sum with a different constant for each value of n. And these constants will be determined by our top two boundary conditions, just like solving any other differential equation. Now, because cos is an even function, we only need to worry about one boundary condition, because they both mean the exact same thing. And the way that we calculate the constants in a Fourier series is to multiply both sides by another cosine function with a different index, m, and integrate across the domain and see what happens. And the reason this works is that the integral on the left is 0, except when m equals n. I'm not going to prove that now, but you can use integration by parts to show it's true. So that means the left-hand side goes from an infinite sum to just one term, and we've got a regular equation we can solve for an, albeit quite a fiddly one. So firstly, I'm just going to introduce a variable k, so we can tidy the equation up a bit and make the algebra nicer. Then we'll start with the left-hand side, which is the simpler of the two. And I think the easiest approach is to use the double angle formula and the fact that sine squared plus cos squared equals 1 to write it like this. Then integrating and evaluating gives us h over 2. So we can substitute that back in. And now let's shift our attention to the right-hand side, which won't be quite so simple. So first we can integrate the cos ky term, which is okay, but we do need to be careful when we're evaluating sine ky. Now, at y equals 0, sine ky is just 0, but at y equals minus h, it becomes sine of minus 2n plus 1 pi by 2, which alternates between 1 and -1 each time you add 1 to n. So being very careful to make sure we get the sign right, that term becomes -1 to the n. And we're ready to move on to the other term, which we'll have to integrate by parts. And when we do that, we get another -1 to the n term that very nicely cancels out the first one, leaving us just with this integral of y times sine ky. Using integration by parts one final time, that y cos ky term is 0 at both limits, so we can ignore that. And we have one last integral to do and evaluate, hopefully with no sign errors, and we've got an expression for our an. At this point, we can substitute k back in, and it might look a bit complicated and unfriendly, but if we think about the dimensions of this, it's gh² times by some dimensionless numbers. And the velocities we found earlier in the 2D case were also gh² times some other stuff. So that's a good sign that we haven't made any big mistakes. And of course we can plug our formula for an into our solution to get it in its final form. And even though it contains an infinite series, if we think about the size of the terms in that series, well, cosine is never bigger than 1. The ratio of the two cosh terms is also never bigger than 1. And we're dividing by 2n plus 1 cubed, which grows very quickly. So that means this series will converge quickly, and we can get really good approximations without having to evaluate too many terms. Now, to compare this solution to the one we found in the 2D case, let's start by looking at the fastest point in the flow, which is when x equals 0 and y equals 0. And that gives us gh² times something which only depends on w over h. So if we fix h, we can plot a graph showing how this changes with w. And we'll do that in just a second. But first, let's see how this behaves when w is either very big or very small. Well, when w is very big, the cosh term gets very big. So the sum tends to 0, and we're just left with gh² over 2, and that's fine. Then when w equals 0, we'd expect this speed to be 0 as well. But cosh 0 is 1, so the cosh term just disappears, and we're left with this. And if this is 0, that tells us that this sum of -1 to the n over 2n plus 1 cubed must be pi cubed over 32. And if you calculate a few terms of this series, it converges so quickly that you can see it is in fact true. How cool is that? We're just trying to work out this fluid flow, and an infinite sum involving pi just appears out of nowhere. And if you like that, well, there's something similar in a minute that I think is even better. Now, let's move on to looking at the average speed across the whole area. And for that, we need to find the flux with this double integral, which really isn't as bad as it looks. If you want to work it out yourself, then have a go before I show you the answer. You should get this with a hyperbolic tan in there now, which is just sine over cosh. Then we need to divide this by the cross-sectional area, and like before, we can take out a factor of gh². Now, hyperbolic tan tends towards 1 as its input gets large, so letting w tend to infinity, the right term will go to 0, and we'll just be left with gh² over 3. But again, let's look at what happens when w is small. Now, because we're dividing by w in there, we can't just set w equals 0 like last time. Instead, we need to imagine w is very small, but still greater than 0. Then we can use the approximation hyperbolic tan of x is roughly x for small inputs. Cancel some bits out, and we're left with this. And setting it equal to 0 gives us this infinite sum, the sum of 1 over 2n plus 1 to the 4 equals pi to the 4 over 96. Another really cool result. And both of these series are brand new to me. There's quite a famous result from the Basel problem that the sum of 1 over n squared is pi squared over 6. And you might have come across that one before, but these ones are much more rare to encounter, even though I think that they're just as cool. So finally, as promised, we can have a look at how these speeds change with the width of the channel for a fixed height h. And we can see the maximum speed approaches its limit quite quickly, whereas the average speed is much slower to converge. Which makes sense because the region of slow flow around the boundary affects the average speed much more than it does the top speed in the very centre. So intuitively, this result seems sensible, and hopefully it means that we haven't made any obvious mistakes anywhere along the way. I hope you found this video interesting and that you managed to do some steps yourself if you were working them out along with me. As always, if you've got any comments or questions, pop them down below, and please consider subscribing if you'd like to see more of this kind of thing. Thanks for watching, and I'll see you next time.